Hi, and welcome to Hardware Design. I am John Brunhaber. So some of the folks who might be watching this might be brand new. This is the beginning of a new term. We had a little bit of a hiatus over the holiday, sort of the end of the winter term, the end of the fall term, and the beginning of the spring term. So now we're back in spring term, and we'll keep this rolling, and we'll try and be good in the summer holiday about rolling this forward. So I thought, since it's been a little bit of a break and maybe there'd be new people watching, that before we picked up on some of the old design that we were working on, so we've been building our micro-polygon rasterizer for a while, and we'd sort of gotten sucked into the nitty-gritty details of doing some verification on part of the unit, that we might just start by building some lower level stuff first. And so I've been trying to build up a library, and I thought a uniform probability arbiter might be a fun thing to have. So to begin, what we need to figure out is, and I hope this is visible for most folks and that you can hear me. So to begin, what we want to figure out is what's going on. So let's see if I have any RTL units that look like what we need. Do I have a fair arb already? Oh, I do. Okay, so apparently I've already built one. So let's start with this priority encoder, because this will be FN mono 16. Having some fun with Emacs. All right. So, and then let's bring up a buffer. So what are we trying to build? So the thing that we're trying to build is an item called an arbiter, and the idea is that if you have a shared resource, so say a bus, and multiple people or multiple agents accessing that shared resource, there's going to be conflicts. So multiple people will go to access that resource at the same time. One way to think of this is sort of like shotgun, right? Is there's only one seat next to the driver. When you and a bunch of friends are going out on a car trip, the way that you decide who sits in the good seat is by yelling shotgun. And if everybody yells shotgun, you need some way of deciding who. If everybody yells shotgun at once, you need some way of deciding, in some fair way, who wins shotgun. So that's the problem that Arbiter is trying to solve. So the way that we're going to represent shotgun is with strings of zeros and ones. So this is still very tiny. So if we had, if we had a sedan, we might have 4 passengers. If nobody wants to shit in the shotgun, there's 4 zeros. If two people bid, we need to decide who wins. So one way to decide is to always pick the person that is the most significant. So in this case, we take a 1 1 0 0 and make it a 1 0 0 0. Similarly, if we had like 7 there, so 0 1 1 1, we would return 0 1 1 1. Boo. All right. So this is kind of at the heart of what we're doing. Now the rub here, in what we've done so far, is sort of a static priority explanation. But what we might want to do is try and keep track of what's going on, and so we might want, some sort of fair arbitration. Because if we look at this example, one of the problems is that if we repeat this example, we get the same result over and over again. So if 1100 bids over and over again, the leading position will always win. What we would prefer is something that looks a little bit more like this, where if the same bid happens over and over again, they sort of take turns. So, you know, if you have two friends that have been traveling with you and they always want to ride shotgun, you'd sort of make sure that they get to alternate. So that's where we're headed. So that's the goal of what we're going to build today, is for this fair arbiter. So on the way to building an arbiter, we're going to need to build a few things first. And we're going to need to decide a few things first. So generally, if we are going to decide priority, what we need is a widget that can determine static priority. So in this case, we want something that implements the first. And then the trick we're going to play is to alter the inputs to that unit so that the effective priority changes. So all good structural design begins with a block diagram. Ooh, and I have Inkscape open from before. So let's just open up something. That button didn't do what I thought it did. So we have a new figure. So what we need, oh, that's horrible. Why would you do those colors? All right, so we're going to give up on Inkscape. So we're going to give up on Inkscape. So from a block diagram, how are we going to accomplish this? So the first layer needs to do something. So what I'll do is I'll shift the inputs. So the idea is if I get an input 1100 and I would like the second position to win, I need to turn it into a 1001, where this bit 2 became bit 3 and then bit 3 became bit 0. Then we can priority encode. So do the static priority. So this is the widget that takes 1001 and is going to give me back 100. And then we want to unshift the inputs. So we want to put them back where they originally were. And so this is going to take 100 and give you back 010. So the input to our block are the bids, which is just going to be an arbitrary length bid string. And the output are going to be the wins, which is the arbitrary length bid string that is now 1 hot. And then 1 hot, for those of you joining for the first time, is a format where one and only one bit in a string is high. So in this case, this is a 1 hot string because only there's only one. Sometimes we'll talk about 1-hot-0 strings, and that's actually what we're talking about in this case, because if there are no bids, there are no winners. So this is one way that we can tell where the resource is going. And I'm just pulling up one of the pages that might have questions on it. Okay, so let's get started. So the easiest thing to go build is the static priority unit. So what we will do is we will start a new module. We'll call it static priority.vp. So we have the VP in the title because we're going to use a Perl preprocessor to help us do some of the heavy lifting. So one of the things that it lets us do is write a single line of Perl that defines a parameter in the unit, bit width. And we'll say the value starting out is 16. And because we're going to use the Perl preprocessor, we have to ask Perl to produce the module name for us. And then we need our parameters. So we'll have input (0). So what the backticks do is they evaluate the Perl expression and return the string that is equivalent. So if bit width is 16, 16 minus 1 is 15. So the Perl generator will put a 15 where this backtick expression is. So we'll call that A. We'll call that Z. Don't forget the semicolon here. End module. Don't forget the end module. This is fairly important. All right, so there's a few ways that we could build this unit. So we'll start with just a straight, table-based implementation. So we'll say always com begin because this is combinatorial logic. We're going to use a priority case statement. Remember to close our case. And then what we'll do is that for each A, so we could say for each A, if that A happens to be 1, then Z is going to be equal to something like 2 to the $I power. So if I is 0, we get 1, and so on and so on. And then this is $BW tick D tick. For my $I equals 0, $I less than $BW. Ooh, we almost messed that up. So the ordering is important here. So we want the highest bit to have the highest priority. So we need this loop to start on BW -1. Then we actually want $I greater than or equal to 0, and then $I minus minus. So what this will do is this will loop in Perl over this line and produce this. All right. So hopefully I didn't mess that up too bad. I did save it to the wrong directory though, so we're just going to close this really quick. We don't need any of the scratch. Yes. So we need to move priority encode. We need to move static priority to RTL static priority. Sorry, a little bit of housekeeping. Some of these things get out of hand pretty quickly. And then we need something to verify with. So what we're going to do is we're going to copy top under prior encode to top under static priority dot VP. So now RTL static priority and verif / top static priority. Static priority. And then we just need to make sure these names are correct. So what I'm doing is I already have a unit that does this static priority calculation. I didn't have to kind of type it out. So what I did was I made a new one and then I copied its test bench. The thing that's what this test bench does is, and I did lowercase a and lowercase c in this one. So we're going to go back and we're just going to change these to lowercase a and z. Just so that life goes a little easier for us. Good. So more or less what the test bench does is it uses some clock signal to every cycle give a random value on A. So it's not too fancy. And then one tick after the clock edge, it checks that Z is a valid number, that Z and A are one hot. So what this says is that Z, the combination, Z better have bid on something that exists. So Z and A would be that intersection. So the winner better be a bid that existed, and there better only be one winner. And then these are checks to kind of clean up some of the extra cases that occur that kind of are playing around with the math that happens due to the static priority. And then maybe we'll comment out our monitor so we can see what it's doing. And then we don't need that. Okay. So make gen module name equals, we said static priority. So now I'm running the Perl preprocessor on the code. It sort of blindly runs on a lot of the stuff. Who is instantiating a DFF? So I might have forgotten how my own makefile works. There you go. So I think this was just slop from last time. So what we should have is in Genesis under synth, we should have the static priority.v, which is the generated Verilog. And what we should get is A0. So we should get our loop unrolled. So if the 0th bit is 1, then we should output a 1. If the bit 1 is 1, and we should output a 2 and a 4. So these should all roughly be the powers of 2. And then this should be 2 to the 15. So let's just make sure that that is true. So we say something like that. Good. So those are equal. Then we could make run module under name equals static priority. So it looks like we had a compiler error. Token is end case. So likely what that means is we forgot a semicolon. We just forgot our default case. So we're not all immune to having a few typos here and there. Forgot our logics. And then we have an implicit port width mismatch. So why do we have an implicit port width mismatch? It is because we forgot to ask how many bits it is. So here in the test bench we said it's 10, but in our design the default was 16. If we were doing better, we would have actually asked in advance what it was, but we'll just trapeze it and then set them both to the same number. Great. So we should have an output now that sort of indicates that things are going the way we expect. We didn't really have any assertions trigger. So you can look at the simulation log. So it doesn't look like anything really bad happened. The other way we could do this is sort of a logic-based implementation. where we sort of just go, and then let's make sure to comment this out. So we can sort of say, well, z at bw is equal, and so what we would do is we just sort of walk through the bits individually. So logically, z, the only way that the most significant bit of z will be 1 is if and only if the most significant bit of a is 1. And then again, we could do a loop. And we could say that any bit I is 1 if and only if, you know, bit I in the input is 1, and note, so we'll say, and there is not, I'm going to be extra generous with parens, so we're going to say not, and what we're trying to say is not any bit above me that is also 1. So what we'll do is we'll do a unary OR across that bus. So that's $BW minus 1 to $I plus 1. And we forgot the minus ones here. So probably have a typo. So we're missing a right curly brace. This is the curly brace we're missing. Ooh. Cannot select 15 to 16. So this actually needs to start at BW minus 2. There we go. So the issue is that the first loop instance was BW minus 1. So, and that matched the case that happened just before it. And BW minus 1 is 15. And then, but BW minus 1 plus 1 is 16. And so the bounds were in the wrong direction. All right. So this was the other way to implement this. And then let's see. What was the third way of doing this? So the third way might be to actually grab a module from somebody else. But I do not have the library API available. So you probably noticed I'm running Synopsys Tools. They have a built-in priority encoder somewhere in there, and so we could just instantiate that module, and then more or less what we're doing is wrapping it so that we could call it directly. This is And if we had a lot of time, what we would do is we'd actually sit down and go through these and kind of go, well, which one produces the best synthesis result? So we could actually synthesize this. Comma equals 1. So what we're doing right now is we're taking the RTL and we're running it through the synthesis tool to map the Verilog implementation to a gate implementation. And then the library we're using is a version of the ASAP 7 library that's publicly available. The tool's not quite publicly available, the synthesis tool, but the libraries to run in the tool are. So if your university or employer has the synthesis tool, you probably could run it. All right. Yeah. So this is the boring part. So we're waiting for it to run. So while we're waiting for it to run, we'll go back to our Scratch. So far what we have is we're going to build something that shifts. We have something that does the static priority. We have something that unshifts. And this was going to be our module. So one thing that we haven't talked about is we need a shift amount. So we need to figure out how exactly we want to do that shift. So one way to do it would be sort of round robin. So if you went to the wiki page on round robin arbiters, it would sort of say, well, what you do is you just increment the shift by 1, or in this case it might make more sense to do -1. And so that you'd slowly move along, and you get sort of uniform probabilities, sort of in the net, as long as the people who are making bids are uniform probabilities, right? So if you don't really have any priors on what your traffic looks like, or if resources are going to constantly compete against each other, it works fairly well. One problem, though, is that if you give it standing patterns, it does fairly poorly. So if you give it something like this, 1, 1, and a string of zeros, and you just kept giving it this string of zeros, it would have a problem, right? And so what I'm saying here is shift next equals shift -1. Is you'd sort of, for a long period of time, have just the leading one winning. And then every now and then, this one would win, and then it would go back. So that doesn't seem very fair, right? You know, if you had a group of two friends who consistently wanted shotgun, and you know, you were constantly sort of giving it to the one guy versus the other, you know, that might cause some heartache. So I've seen some interesting schemes in the past here. Some of them involve instead of decrementing by one, decrementing by some interesting prime number. So if we're 16, you know, decrement by 7, and then it sort of ends up having an interesting walk. So you kind of randomly walk through the shifts, and then that's kind of interesting. You might actually hook it up to an LFSR, so a linear feedback shift register, and look at that. The approach we're going to take is we're going to actually shift to make the last winner the lowest priority. And we'll make this notes, txt. Good. All right. So the last thing we'll take a look at before we sort of move, before we call it a night, is what the synthesis result is. So next time what we'll do is we'll build the shift unshift unit based off of this last winner thing, and then we'll hook it all together to build an early version of our priority encoder. So it creates a Verilog file that represents the module. So it looks similar to what we had before, you know, static priority, A equals 5. This is there. This is interesting. So it looks like it is, because I didn't, so it looks like it's just shorted these two wires. That's probably what we would like it to do in general. You know, but we may need to actually add constraints later. But otherwise, you know, it's just a sea of gates. Not too many gates, and not surprisingly, a lot of them are NORs and inverters. And then ANDs and inverters. So pretty close to what we wrote. It seems, you know, I would hope that it's doing some sort of sharing. So I'd expect that, you know, maybe N31 gets consumed multiple times now. You know, does N32 get consumed multiple times? It does. So it looks like it is sharing some of that OR network. So if you go back to our implementation, the way we wrote it is that this is a huge OR gate, but it shares sub-ORs with other expressions. So we'd expect those to all be put together. Other interesting things is it doesn't seem to have used, it has used a NOR 4, so it saw an opportunity to do a bunch of NORs in parallel at once. We could also go look at its design cost. So reports, QOR.report. So we had 11 levels of logic. Does this sort of make sense? Well, you know, we think that the worst case is going to be something like log 2 of the bit width plus, you know, one gate for that AND, which would be about nine logic levels. You know, so if you throw a few inversions in there, that easily gets us to 11. The critical path length is in picoseconds, so it's 122 picoseconds. There were 40 cells. You know, is that a third of them were inverters? So that means that 2/3 were not inverters. And then this was fairly small. It was 37 microns. So this is a relatively tiny unit. So that is a static priority. So some of you who were watching may have noticed that this is one of the assignments in class. You know, feel free to go ahead and use this for your homework. Make sure you understand how one of the other two implementations work. And next time, what we'll do. So next time on hardware design, we will implement a shift based on prior winner. So normally the way I do this is that I would encode the winner with a decimal to implement the shift. But I think this time what we'll do is we'll do a direct shift based on the 1 hot value. Based off of the prior cycles 1 hot value. So that prior cycle means we're going to have some sequential components, so we'll look at using the D flip-flop next time. Cool. So if there are any questions, I'm happy to answer any before I run in the next couple of minutes. There should be a live chat dialogue where you can you know, ask questions here. But if everyone is good, we can call it a night. I think most folks are probably happy. If you found this helpful, the video will be archived with some of the other streams that we have before. So feel free to tell your friends about it, and we will try and pick this up next week, barring any sort of unforeseen circumstances. Thanks for tuning in. Have a great night, and see you next time.